Welcome back to the Deep Dive, where we tear apart the most earth-shattering scientific papers and figure out why they still influence, the research you read and the technologies used today.
Today, we are diving deep into a paper that really provided the essential instruction manual for modern quantitative biochemistry. It's the 1951 masterpiece by Lowry, Roseborough, Farr, and Randall, titled Protein Measurement with a Folin Phenol Reagent.
Right. And if you've ever been in a wet lab or even just read a paper about enzyme activity, you know you have to quantify protein. It's fundamental. This paper established the method, the Lowry assay, that became a pillar of the field for, half a century?
It truly did. And the historical context here is really crucial. The core chemical, the Folin Phenol Reagent, wasn't new.
Oh, really?
No, it was proposed decades earlier, back in 1922 by Otto Folin and Wu. It showed a lot of promise. I mean, amazing sensitivity, simple procedure, but it just hadn't caught on. People found it a bit temperamental.
So the mission of this 1951 paper wasn't really invention, it was more like taming.
Exactly. Taming is the perfect word. They took this difficult, quirky reaction and figured out every single variable, the pH, the timing, the concentrations, to enable its, and this is their phrase, fullest exploitation. They turned a novelty into a tool.
And what a tool. I mean, the sensitivity they talk about is just remarkable.
It's incredible. They describe procedures capable of measuring as little as zero point 0.2 gamma of protein.
And for anyone not up on their old school units, zero point 0.2 gamma is 0.2 micrograms.
Precisely. Microanalysis territory. To reliably detect protein at that level in 1951, before all the modern equipment we just take for granted, it's astonishing.
It just fundamentally changed the kinds of questions researchers could even ask.
It gave them a massive advantage. But all this sensitivity came from a combination of two distinct chemical processes. You can't just throw the Folin reagent at the protein. You have to prep it first.
Okay, let's unpack that, this two-step process. Walk us through step one. What's the prerequisite for getting that color?
So step one is the alkaline copper treatment. They used a specific mix they called Reagent C for this. Basically, you mix your protein sample with copper ions in a really alkaline solution.
Right.
This is where the magic really starts.
The copper preparation, that's the key to amplifying the signal, right?
It's everything. How significant is it? Well, the raw Folin reagent mostly just reacts with a couple of amino acids, tyrosine and tryptophan. But when you add copper and alkali first,
What happens?
you get a massive 3 to 15-fold increase in the final blue color. The copper is a sensitizing agent. It lets the next reaction pick up signals from the protein's peptide bonds, too.
So the copper isn't just helping out, it's the core multiplier that makes the whole thing so sensitive.
Exactly. Without it, you're missing most of your signal.
Now, I know there's another copper-based test, the Biochemistry reaction. Is this related?
It is, chemically. The Biochemistry is also based on copper complexing with peptide bonds. But, and the authors are very clear about this, they are not strictly proportional. The mechanism is different enough that you can't just, swap a standard curve from one to the other.
That's a really important distinction. It shows they were being meticulous. So how much copper do you need for this to work?
Actually, a very small amount is enough. Their calculations showed that of all the places copper could possibly bind on a protein, only about half of them actually lead to a big reduction of the Folin reagent later.
And those are the ones that matter.
Right. And it seems that specific fraction has a much stronger affinity for copper anyway. So it's a very efficient process.
A smart use of the reagent. And how long does this first step take? Are we talking hours?
No, it's pretty quick. It's nearly complete in about 5 to 10 minutes at room temperature. They did note you can heat it to speed it up if you're in a hurry, but it doesn't actually change the final color yield for this part of the process.
Okay, so step one primes the pump. Then step two is the payoff. The prepped protein reduces the Folin reagent.
Reagent E, the phospholipid phosphatenzistic acid mix. And this is the stage where all those notorious procedural requirements really kick in.
This is where timing becomes, everything.
This is why the paper was so necessary in the first place. They had to standardize these critical peculiarities.
So their standard procedure could measure, 5 to 100 micrograms of protein. But standardization has to start with a good comparison. What did they suggest for a working standard?
They recommended using human serum, but they also included a now famous warning about one of the most common proteins in any biochem lab, crystalline bovine albumin.
BSA, what was wrong with using BSA?
They found that dilute solutions of it were, highly unsatisfactory. It turns out they have a marked tendency to undergo surface denaturation.
Meaning the protein just starts unfolding and clumping to the sides of the tube.
Exactly. And if that happens, your standard is no longer consistent, and your whole calibration curve is garbage before you've even added a single region.
Yeah. That's a huge insight, a real game changer for getting reliable results. But the most crucial detail, the one that made the assay so tricky before 1951, was the mixing.
Ugh, this is the defining terror of the Lowry assay. When you add that Folin reagent, you only get the maximum color if the reaction happens at a very specific pH, right around pH 10.
Okay, so you need to control the pH.
But here's the problem. At that optimal pH, the Folin reagent is incredibly unstable. Its reactivity loss has a half-life of just 8 seconds.
8 seconds, that's nothing. I mean, by the time you've pipetted and capped the tube, you're already losing signal.
It's completely unforgiving. They figured out that a delay of even a few seconds in getting it all mixed together would just tank your final color reading.
That sounds like a nightmare. So how did they get around that impossible time crunch? They must have designed a really specific buffer system.
They did. They solved it by using a very specific mix of sodium hydroxide, the NaOH, and sodium carbonate. The NaOH neutralized some acid, and the sodium carbonate buffered the whole mix right around pH 10.
And that combination was the secret sauce.
It gave a much more stable color than using either of those reagents by itself. It gave the technician a narrow, but at least functional, window to get the job done.
Okay, so once you get through that stressful step, the blue color develops over about 30 minutes. Then you take the reading. You mentioned they read it at different wavelength.
Yes. For your lower concentrations, say 5 to 25 micrograms per mil, you read it near the peak absorption, which is 750 nanometers. But the test is so sensitive that a strong sample would just max out the spectrophotometer.
It would just go off the scale. So what was the fix for that?
For the stronger solutions, they just switched the wavelength to 500 nanometers. The color absorbance is weaker there, so it keeps the reading in a workable range. It's a really pragmatic solution.
That's just smart lab work. Okay, now let's talk about the worst case scenario, stubborn samples. Specifically, proteins precipitated with strong acids.
Ah, yes, the dreaded acid precipitates. They are chemically locked down and are notorious for being hard to redissolve, especially if they've been dried out. And if the protein isn't dissolved, you can't measure it accurately.
So what was the Lowry paper's nuclear option for those samples?
You have to hit it with stronger alkali, 1N-NaOH. For small samples, a few hours at room temp might do it. But for bigger, tougher ones, you might need to heat it at 100 degrees Celsius for 10 minutes or more in that strong alkali.
And that harsh treatment has to come with a cost.
Oh, a significant one. They noted that samples heated like that yielded final color readings that were only 82% of what you'd get from a non-precipitated sample. You were deliberately destroying 18% of your potential signal.
But why would you do that? Why would any researcher intentionally kneecap their own sensitivity by almost 20%?
It's the classic trade-off between sensitivity and certainty. If you try to measure a sample that's only partially dissolved, your result is guaranteed to be wrong. It's an unreliable low number. Whereas if you sacrifice some of that color potential to guarantee that 100% of your protein is in solution, you ensure that whatever number you get is an accurate relative measurement for that whole sample. And in science, certainty often trumps raw sensitivity.
That is a fundamental choice you have to make in the lab. Okay, let's shift back to the extremes of analysis. What about that breakthrough microanalysis capability?
This is where they really showed off what the method could do. They used a customized Beckman spectrophotometer, adapted for tiny volumes, down to 0.05 milliliters, and they got reliable measurements of 0.2 micrograms of protein.
And even at that tiny scale, the geometry of the tube mattered.
Right. They had to use these special slender tubes, only 3 millimeters wide. If the tubes were too wide, they said you'd get low values. It just speaks to how sensitive the whole thing is to every little detail.
So it demands extreme rigor. But for all its power, the authors were very open about its flaws. What are the big disadvantages?
The first one, and it's a big one for standardization, is the variability between proteins. The method just doesn't treat all proteins equally.
What do you mean?
Different pure proteins give you very different amounts of color. They saw extremes with trypsin and gelatin. They differed by a factor of 3 in their color yield.
A threefold difference. Wow, so if you're measuring a complex mix, like from a cell, you can never get an absolutely accurate mass.
Never. You only get a value relative to your standard. This is why you always have to report your results as, say, equivalent to bovine serum albumin. It's a known limitation compared to something like the Biochemistry reaction, which is much more uniform.
And the second flaw was linearity, right? We love straight lines for our graphs.
And unfortunately, the Lowry assay doesn't quite give you one. The relationship between color and concentration isn't strictly proportional. It
Yes.
means you can't just run one standard and use a multiplier. You have to run a full, fresh standard curve every single time you do the assay to be accurate.
So with all that complexity, the timing, the curves, the variability,
Yeah.
why did this test take over the world? What was what that made it superior?
It just came down to performance metrics that were revolutionary for the 1950s. It is 10 to 20 times more sensitive than measuring UV absorption at 280 nanometers, which was the main alternative.
And UV absorption has its own problems, especially with messy samples.
Precisely. The Lowry method is much more specific to protein and is far less bothered by the turbidity you get in raw biological samples. Plus, it's about 100 times more sensitive than the simple Biochemistry reaction.
And what about compared to the 9-hydrogen test? That one's sensitive too.
It is, but the 9-hydrogen reaction actually gives a stronger signal for free amino acids than for intact proteins. The Lowry is the opposite. The Folin reagent gives more color with the proteins themselves, making it much more useful for what people actually wanted to measure.
Okay, let's tackle the final practical hurdle for any biochemist interference. What common lab stuff messes this assay up, and what, surprisingly, doesn't?
So the good news, and this is a huge selling point, is that very few substances you'd find in typical biological work cause serious interference. They even tested it on whole, non-extracted tissue and found the error was only about 3 to 6%.
That's low enough for a lot of applications, but there must be some specific bad actors.
Oh, absolutely. Things that react directly with the Folin reagent. Uric acid, guanine, and xanthine are big ones.
Things you'd find in a cell extract.
For sure. Guanine, for example, gives about 50% more color than serum protein by weight. So if you have a lot of purines in your sample, your protein reading is going to be artificially high.
That's a huge potential error. But there was a weird chemical quirk there, they pointed out.
Yes, the difference between guanine and guanosine. Guanine reacts strongly, but if you just add a ribose sugar to it to make guanosine, the reaction curiously disappears almost entirely.
Strange. So what about things that actively suppress the color?
The big one they cited was glycine, a common amino acid. At just a 0.5% concentration, glycine can cut your protein color in half. Also, high salt concentrations, like ammonium sulfate from a purification step, can decrease color development.
That ammonium sulfate issue must have come up all the time. Did they have a fix for it?
They did. They realized the salt wasn't really reacting, it was just lowering the alkalinity below that critical pH 10. So they found you could just compensate by adding a bit of extra alkali. Another procedural fix for a chemical problem.
And it's probably worth mentioning some of the common things that don't interfere to reassure people.
Absolutely. The list is pretty long and robust. Urea, sodium tungstate, neutralized acids like perchloric and trichloroacetic acid, and even some common solvents like ethyl alcohol and acetone.
That robustness is really why it was adopted so widely. So wrapping this all up, where did Lowry and his team say this method should be used to get the best results?
They laid out 4 ideal applications. First, measuring protein during enzyme fractionations, where what you really care about is the relative change from one step to the next.
Makes sense. What else?
Second, measuring mixed tissue proteins where an absolute value isn't critical. Third, analyzing really tiny amounts of protein or very dilute fluids like spinal fluid, where other methods just weren't sensitive enough.
And the last one, which is perfect for high throughput work.
Exactly. Analyzing large numbers of similar protein samples, like antigen antibody, precipitates in immunology. Once you nail down the procedure, its consistency and speed were indispensable.
So what Lowry, Roseborough, Farr, and Randall really gave the world wasn't a new chemical reaction. It was the roadmap. The precise pH, that critical 8-second window, how to handle interference to turn a finicky reagent into a revolutionary tool. They unlocked a new level of sensitivity for labs everywhere.
And that brings us to our final provocative thought from this paper. We talked about that harsh treatment for stubborn samples, heating them in strong alkali, which sacrifices about 18% of the potential color. This raises a really important question for any researcher. Does making that sacrifice to get a stubborn sample completely dissolved still give you a more reliable relative measurement than trying to analyze a sample that's only partially soluble?
A completely dissolved, slightly degraded sample versus a partially soluble one with maximum color potential. That is the high-stakes trade-off this 1951 paper forces you to confront. And making that choice correctly is often what determines whether your experiment is reliable or just plain misleading.